Oh,
I still can't get my wife to watch your lectures on YouTube. She doesn't seem to be nearly as interested.
I mean, you should say that I'm not a celebrity yet. I'm only 46 subscribers, so he doesn't have to. It's all weird because I would like to take away the ads that come up in this. So you would like to take it off, but then there is a limit on how many subscribers you have to get rid of the. It's weird.
My rule is if I have to sit through an ad and I can't skip it, or, especially if it's a longer ad, that is a product that I will not utilize.
Reasonable. Microphone. Mathematica doesn't count, right?
What's that?
Using Mathematica doesn't count to get some integral.
It did not provide an easier result, that's for sure. And then I looked through, I had a set of the translated Russian integral tables.
Yeah, that's Tim.
And I couldn't find anything in that. And of course, CRC.
Have a homework. Speak today. I had to post a new one. Today. And should we have a homework due on the day of the exam? You guys don't speak out, I will put it.
I think no.
Okay. So no. But I can make it due in the next day, Tuesday. Which probably means that maybe everything covered as of now is what. But then remember that I can even ask a Lagrangian problem in the context of pretend that I'm asking a functional derivative problem, because it's the same idea you put it in. It's just the context will be new. So it doesn't, I can influence the class, but I'll try to ask all the questions so that we have covered. Okay. So homework 4, let's say, is what is it?
22nd.
22nd.
The only reason I know that is because I'm off on Monday. Right.
What is the occasion?
President's Day.
Oh, okay. Oh, we should have come later. Since when do we have the President's Day as a holiday?
I don't know if SIU does, but my school does.
No, we don't have it, but I was saying in US, since when do you have it? Yeah, but why was it so important to make it a holiday? If presidents, which president is it? Is there any president? These days, the president doesn't seem to be that.
I don't know when it started.
So just curious. It's not a specific president, right? All the presidents. Just curious. Okay. So we want to do another example today. Hopefully, the last example before we do the action principle or the classical mechanics part of it. So this is called Brachistochrone problem or just Brachistochrone. I think it's called Brachistochrone problem. It's a class of problems. It doesn't have to be in the context that we do talk about. So let's say we do agree that if we're going to work in constant gravity, so that is G acting downwards. Right, so that's here G. We have 9.8 meters per second squared. And yeah, so here's a quiz before we begin. Okay. The quiz is that how will the whole of the discussion that we are having change, let's say in another planet? That means to say if you change G, how is this going to, so if you were to, so we have the Brachistochrone curve that we will derive here for this particular G. And then you say that if you go on Pluto or Jupiter doesn't have a flat surface. So that, but let's say if you're on a constant radius surface, then does the equation of the Brachistochrone change on another planet or another exoplanet, right? In another galaxy. So that's a quiz. So if you have constant gravity, one thing that happens is that everything happens in a plane. Once you, or maybe I should, there is one restriction, right? If I have no initial velocity in the direction perpendicular to G, then everything will remain in that plane, right? Most of, is this correct? So the question is, if you, in a uniform gravity, the motion is always in a plane, is that a true statement? Can you repeat the question? So if you have a uniform gravitational field, right? Right. So gravitational field is constant everywhere. Imagine that it's on the surface of the Earth, which is surely true as far as you're within 10 kilometers or so. To do significant digits, it's correct. But let's say it is really uniform everywhere. And now you drop a particle or you throw a particle, will everything happen in a plane? The motion will be in a plane. I think that's correct.
So. Sounds right. I think the way, like, when they address it in the engineering mechanics, I mean, even if the problem's supposed to be three-dimensional,
yes,
you can always just turn your perspective,
exactly,
so you keep it.
But it is two-dimensional, right? Then generically, I was almost thinking that there might be a component coming out, but then even non-uniform gravity, right? It's a plane. Angular momentum is conserved.
It's only when you get like a
like orbits, right? Orbits are
Coriolis force involved or something. You have to.
Coriolis force, but that's a coordinate system dependent on it. If I'm in a uniform inertial frame.
Well, I just mean there'd be another acceleration.
Yeah, so you're saying that the surface is moving. Yeah. But let's say it's rolling. I think, yeah, second, this right is I'm not very sure. I'm a little concerned that I'm not making that right. But I think the correct statement, I think, is that angular momentum is conserved in uniform gravity and, for that matter, any Newtonian gravity. And if angular momentum is conserved, if you're in that plane or P crossed with L, sorry, P dotted with L will be 0. So I think that's the argument for the orbit being in the plane. So, but be critical. I'm a little suddenly intuitively I feel, oh, maybe it's not correct. Yeah, so to avoid that, I will say that we are in a plane. Like, let's say we drop something in this plane, just to avoid that small issue, but I feel that's not necessary. Okay, so the idea is that you have a point x1, y1, that's your initial point. So everything is happening in a plane. So there's only 2 coordinates are needed. And at this point, velocity v1 is equal to 0. And again, that's not necessary. That's for simplicity I'm doing it. A very simple extension of this problem is that what if v1 is not equal to 0, right? When you think of an exam problem, like I can say, oh, I did for v equal to 0. How will it change for v1 not equal to 0, right? That could be a question in the exam. How will it change for g being some other planet? Like, these are the simple problems I can ask in an exam for. Like others, I think I've taken my exams for Abdullah and Aryan. Like, reasonably simple, which you can do it, but it requires complete understanding of the problem that you have done. So that's what, at least I try to make questions like that. So that's what comes in my mind. So ask that question, what if v1 is not equal to 0, but we will do v1 equal to 0, and then we drop it. And if we require that the particle has to go through another point x2, y2. And then you say that, okay, it won't go, right? I mean, if you drop it, it will go straight down. But then you want it to go there, so you want to keep it. Let's say you have a surface. So you can think of it as you're building a roller coaster, right? You're thinking of building a roller coaster, and you want to build it in such a way that the time taken from x1 to y1 or just rolling down, like rolling or sliding down. You can say, if you don't want to consider friction, you say that it is rolling down, sliding down without friction. But if you perfectly roll, then that's the same effect. Like, as far as the time is concerned. I'm questioning myself better. New question. So if you have a sliding motion, so this is sliding without friction. That's one motion possible. And the other is perfectly rolling. And I don't have to say friction. If you have to roll, you need friction. Right? Without friction, there's no possibility of rolling. What's the time difference between these two? Is it the same, or?
Sliding without friction would be the quickest.
Correct. Because I is equal to the moment of inertia, it doesn't come into picture at all. There is no rolling at all. So I think the question then here is that you allow rolling, but then you stick to this kind of problems. You don't compare sliding and roll. If you're putting in friction, keep that constant, and then you ask which surface is having minimum time. If you're keeping friction, keep it, then you're talking about rolling. If you're having sliding, so either of these two are possible. That's what I'm trying to say. Usually you would do it for this problem, at least first time in Brachistochrone what was done. It was done for this problem, but My claim is that it will work through for this also, except that the time itself will be different, but this path will have the minimum. Like, again, be critical about that, but if we want to avoid that discussion altogether, we can say this is frictionless, and let's say this is slow. Like then we don't have to, if there is any confusion as to, oh, that doesn't make sense, right? If the time is different, how can it be minimum? Relative to these two, there is a difference, but if you stick to one of them, Brachistochrone, or we are asking the question, what should this design be of a roller coaster platform that will take you from one point to the point in the least amount of time? Is the question clear? Okay, any concerns? Okay, so that's what you're asking. Somewhere in between, let's say there is x comma y, right? That's just an arbitrary point on the surface, and we have conservation of energy. So of m kinetic energy, v1 square. That is only gravity here, but then there is a normal force, correct? So there, at each point of this, there will be a normal force, and that is mg acting downwards. Is there any other force? Mg and that's it. I suppose. So mg, the work done by gravity is the potential energy. So that's mg times y1, right? It's only the vertical coordinate that contributes. What about the work done by the normal force? Right? We should have an energy associated with the normal force also. What's the energy, or what's the work done by the normal force?
0 here.
Right, 0, because it's perpendicular, right? At every point, the path displacement is 0, so it doesn't do any work. So we don't have to worry about all through this. So energy conservation requires that this should be half mv squared plus mgy. Right? So that's arbitrary. So that's a conservation statement between those two points. V1 is 0. So this is equal to 0 because of the initial condition. That's what would change. If you were to change your system, if I ask what happens, then that's what would change. Mass can cancel out. And I can write this as v squared is equal to 2 times g times y1 minus y, which means velocity itself is square root of that. So that's it. We are interested in the time taken from here to here. So time taken would be equal, or let's say dt for a small element of, this is ds, and the time taken to go a small tiny displacement ds is ds over the velocity at that particular coordinate. That's a statement of velocity, and then the total time then would be, so total time t would be go integral of ds over v, start from x1 comma y1 and go to x2 comma y2. ds here is the line element, the distance you go into that plane. That's dx squared plus dy square, and ds by dv then, ds by v is dx squared plus dy squared divided by 2 times g times y1 minus y. So the total time taken for a given curve is equal, so total time taken. Now I have to decide on a function of as a function of y for time being. Let's say that seems to be the natural thing to derivative. So this is y, right? So I can either say this curve is y as a function of x. So I can either say y is a function of x, right? That's the curve that I can specify. Or I have another choice that I can say this is y and x is a function of y. Either one is the same, right? There is nothing special in the direction of, actually there's something special in the direction of y in the sense that g is in the direction of y, so y is surely special, but nothing stops us from saying that x is a function of y. So is there any advantage between the two? So first, let's say that's a natural thing, right? That's what we always tend to do. Natural in the sense of the way we have studied or we have written our textbooks. So that's seems to be equal to x1 to x2 dx. Take the dx out then, and we have 1 plus dy by dx whole square. It's 2 times g y1 minus y. But as I said, one might say, oh, why do this? Let's also think of t as a function of x. That means to say x as a function of y, right? Either think of y as a function of x and x as a function of y. Then you would say this is y1 to y2 dy. And then this is 1 plus dx by dy now, whole square, divided by 2 times g y1 minus 1. Okay. Both are true expression, both whether I minimize this or minimize that, they should correspond to the same solution as far as construction of this roller coaster is concerned. It should correspond to the same answer. It's just that one should be the inverse of the other. But now that we have studied functional derivative, what will be the difference between the functional derivative of these two? Now that you've done a reasonable number of examples, we are going to talk about minimization of these two functionals. And what's the striking difference between the two? Congested there. In terms of simplicity, let's say.
The second one is.
That's correct. And why do you say that? That's a correct answer. At least that's what I would also say, yes. What you mean probably is that there are two y's here to differentiate in the denominator. And here, if you're differentiating with x, there is only one x. So two places, when you think of a differential equation, it will be two terms in the differential equation. Of course, you can process it and get it back, but this will be a lot more immediate. So this one will be a lot more immediate than this. Good point. So that's exactly what I want. A very good observation that this has two y's. Is that very clear to everyone? So there are two y's, differentiation of two, and there are two quantities here to differentiate. What is it? Numerator and denominator. There are two terms here. That differential equation will look, or it will require more processing to reach a solution, and here it will be a lot more immediate. Okay, good. So with that observation, let's proceed. I can. So take So our goal is to find the minimum value for this time. So for, of course, our suggestion is that L of t of x respect to the of x of y has to be equal to 0. That's our condition for minima or extrema. So that's equal to, first let's evaluate this. Pretend we are taking a normal derivative. So this is x1, y1, y2, ty. And I have to do this derivative. So it is the numerator has, first of all, is 1/2 times 2 times of, let's say, prime x over dy prime. Things go in the denominator. It's 2 times g y1 minus y, that stays intact, y prime actually. And this comes in the denominator, so it is 1 of x. And finally, this has a derivative d by dy prime, delta of x of y prime. That's clear. Too many things, but we have done enough examples that I can. Okay. Okay. Clear? This is a derivative of a delta function. So I know how to evaluate the derivative of a delta function, put the derivative on the other side and put a negative sign. So this implies immediately that d by dy of, so that's the d by dy. This is delta of y minus y prime. So delta for derivative of a delta function is negative of the derivative of whatever else is there. So this is 1 over 2 times g y1 minus y now square root dx over dy over now that has to be equal to 0. Right. And that's the simplicity I'm talking about. This came out as a derivative of something is equal to 0. Here, this will be derivative of something will be equal to something else. And which probably, or which I'm sure can be combined together to get into this. But it's a few more steps that, especially if you're in a new problem where you don't know the solution, then it might take more intuition to see that simplification. Okay. Any questions at this stage? Okay, so if this is equal to 0, that means this is a constant. So you say this is 1 over 2 times g y1 minus y. And this is dx over dy divided by 1 plus x over dy whole square. This has to be equal to a constant. So let's put the constant in such a way that at least dimensionally they are correct. This is dimensionless, x and a y, two distances. This is dimensionless. This has the dimensions of, this is what gives you the time on the right side, right? So this is acceleration of the distance. So this is 1 over velocity there. So let me, just to take care of the dimensions, this is a constant. I can write anything I want. So this is 2 times g and y1 minus y. So let's say, I will say 2 times r, I suppose. Okay. this will have something to do with the solution you're getting. Naturally, we should have said that this is some distance, right? It will come out as R is going to be the radius of some circle. So that's a diameter in that sense. But that is looking forward into the solution. So at this point, I'm just motivating it dimensionally that there has to be some length here. So I'm just saying there is some constant R there, and I think it's 2 times R just for simplification. So 2 times G cancels out, right? That's the way I have constructed it. It's not that it is, it got absorbed into R if you want. Okay, so that's what we have. Let's square this. So this is dx over dy squared is equal to y1 minus y over 2 times r. So that's what I'm going to square, and then there is 1 plus dx over dy squared. So that gives me a differential equation. So put this on the other side. So I have dx by dy is equal. This became 1 minus that, and this still stays there. Square. One minus. So square root of that will be square root of this, but then let me swap it, both are the same. So that's equal to, did I do this correct? Yeah. So I divide both terms by this, right? So it is 2r over y1 minus y minus 1. So dx is equal to dy over 2 times r okay. So that's a linear differential equation. If you want dx by dy is equal to so much, in fact, we can integrate this, right? So now it is what's it called? Separated out. All the y's are on the right side, all the x's are on the left side. So this can be integrated. We can go from x1 to x2 here, y1 to y2 accordingly here, and we should get the solution. But just to motivate the solution at this point, we can of course do mechanical substitutions there. But just to appreciate the solution, let's go and think about what a cycloid is. The solution is going to be a cycloid. So let's discuss a cycloid for a few minutes. Any questions before I do that? So we have a construction of the problem. This is where the functional derivative operated. Like this is what we have studied. And rest is basically mechanical integrations, which we should all be familiar with, or just like practice. Correct. Comments? Okay. Well, let's leave that for a minute. Let's talk something independent. Let's say cycling. Spelling, hopefully. Yeah. And cycloid, I'm going to talk about an inverted cycloid. We can actually have a normal cycloid also. So let's say there is a straight line, and think of a wheel. This is a wheel that's rolling. That's your rolling omega, and it's perfectly rolling. Remember that what that means is that if you have a velocity v here, that's your v, And what I'm talking about is that if you go a little earlier, that's where the circle was. So that's my x1, comma y1. That's where the wheel started rolling, and this point now reaches somewhere here. That point here after rolling reached somewhere here. And that's angle theta. So it evolved. So this point, if you were to imagine, they will actually go along and curve. And that's what we're talking about. So let's say that's x1, y1, and this new point is x comma y. Is the diagram clear? So this from x1, y1 reached this point here, xy, as this rolled. So if you had to think of this as S is equal to r times theta, the amount that it has evolved in this direction is exactly r times theta. That's the condition for perfect rolling. S could be less than r theta, and S could be greater than r theta. Right? So this is perfect rolling. And this is what will this be? So this means this is small. So S is 0, right? It doesn't move at all. So this is like spinning. Like so that means so this is what happens in spin. So this is spinning. Also, I like to call it slipping. And this one is, there's a lot of S, but there is no very, say, small theta. So the S motion is significantly larger than theta. Take it to the extreme where theta is equal to 0, so no rolling. So this is what happens in ice, right? And this is called sliding. It is not able to roll at all. Right? That's the three cases possible. Right? Again, unrelated or different question. When it is perfectly rolling, wheel is perfectly rolling. Think of a bicycle wheel. You just push it, and after you push it, there is no engine attached to that. Just one bicycle wheel. In what direction is the friction acting? Is the question clear? Okay. So is it in the backward direction or is it in the forward direction? Let that be a quiz. Sure. Okay, so we are talking about we want to talk about x comma y, and we are here, right? This is what we're not talking about snow and ice. All those could be extensions, right? How does this change if this? But I think they will be hard. These are usually harder problems. The moment you put in an inequality, things get significantly harder. Okay, so what is x comma y in terms of x1, y1? Here, because s is equal to r theta, this immediately implies that take a derivative with time. So ds by dt is equal to r stays the same, d theta over dt. That means v is equal to, that's omega, right? R times omega. So this v is omega times r, so they're related. That's what it means. So this point is moving with respect to time. So that's velocity times time. So let's say what is x, right? We want to write what is x. Instead, let's say what is x minus x1. So x is this distance. Oh, sorry, this is x, right? So this tiny distance. Subtract out x1. So x minus x1 is this tiny evolution here. That will be equal to how far this center goes minus this sine theta. So check it out. This is equal to velocity times t as a function of time minus of r sine theta. velocity times t is equal to omega times r times t. Omega times t is nothing but, so angle theta is equal to omega times t. That is r times theta. So this is the same as r times theta minus sine theta. What about y? We are talking about y minus y1. Again, look into the diagram. Y into y minus y1 is this feature here. So let's say it is y1 minus y instead. Y1 minus y is equal to, that's your total r minus r cosine theta. So that's your equations for cycling. You just read out from the geometry of this rolling motion. And let's so some properties. So this is your equations of cycler. Let me rewrite this. So yeah, so let's write this as x minus x1 over r. Like always, that comes in that combination, and I want to write. I want to write it as equal to theta minus sine theta and y1 minus y over r is equal to 1 minus cosine theta. That was an immediate rewriting. That whenever we have a sine theta and a cosine theta coming in, it's good to think of a circle, right? There is some circular motion in here, something connected with the circle. So let's write sine theta is equal to theta minus x1 over r, and cosine theta is equal to 1 minus y1 minus y over sine square theta plus cosine square theta is 1. That seems to suggest that 1 minus y1 minus y over r whole square cosine square theta plus sine square theta, that will be equal to theta minus, but you don't want to write theta itself, right? Because then there are 3 variables. So you want to solve for theta in terms of the y term. So it is cosine inverse of 1 minus y1 minus y over r minus x minus x1 over r. So that's the equation. A cycloid purely in terms of x and y, but almost everywhere intuitively this is much more convenient. Right? This is, if you redefine your variables, this is x, like if you redefine your variables as x1 is equal, you start from the origin, right? x1, y1 is 0, then it is clear that x minus the velocity, so how fast you're going, right? So x minus that is sine theta and y is cosine theta. So you want to visualize this as x, how do you say, x minus omega t, or x minus theta is equal to minus sine theta, let's say, and y is there a 1? I think it's 1 minus cosine theta. That's okay. 1 is just again because you put your origin there. If you had put the origin here, right at the center, where the center of the circle is, then that 1 also belongs to there. And that's the idea of a circle, which is actually moving as a function of time. But this looks much more complicated, but we want to keep this form because whenever we say the structure, we should be able to say that, oh, that's a cycloid. And we are going to start from here and reach there. So So that's one thing, but we also have a differential equation there, dx and dy. Is that possible to motivate from there? So let's reach that. Let's do that also. So we have this equation here. Let's take dx with respect to d theta. So that's 1 over r. Yeah. X1 goes to 0, dx by d theta here will be equal to 1 minus theta is 1, so this is cosine theta. That's that's coming from this equation. So that's implies that. Do the same thing with y1. You have dy by d theta, and that is the 1 over r. That's equal to when you take a derivative of a cosine, there is a minus sign, and I think there's a negative sign here, right? Derivative of cosine gives you negative, so that's a positive, but then left hand side is negative, so that's let's do this. We are interested in dx over dy here. So let's take a ratio. Each one is a single variable quantity. X is a function of theta, y is a function of theta. So there are not two variables, so we don't have to worry about partial derivative. So we just take a ratio and we get dx over dy is equal to minus of 1 minus cosine theta over sine theta. 1 minus sine theta is, 1 minus cosine theta is 2 sine square theta over 2. And this is 2 times sine theta over 2 cosine theta over 2. Sine theta is cancelled, 2 cancels, so this is equal to minus tangent theta over 2. But I have to write it in some other form. Let's see. So it's good to stay in theta itself. So let's now see 1 minus, yeah. So this is perfectly fine, but we would like to connect it with this equation somehow. And this is in a half angle, so we have to stick with the first angle. So that might be more convenient. So even though there's a simplicity in that, so maybe this can be processed in some other way, possible. But in the blunt way of doing it, so let's go back to this equation and see if we can process it. Okay, so this is equal to, let's say, dx by dy is equal to minus of 1 minus cosine theta over sine theta is nothing but square root of sine square theta. That's 1 minus cosine square theta. And so this is 1 minus. So this is equal to minus, suppose I say this is square root of 1 minus cosine square theta. This is 1 minus cosine theta. Simplification, so that's 1 plus sine theta. Okay. So, okay. Keep the steps going from there to here. I'm almost like matching. Okay. Let's start from here. So that's how about this? We stop here, right? We stop at this stage, and this is our observation about site Y. Right? Now we go back there and see whether we can process that into it site Y. So let's go there, and this is dx. We want to do an integral, right? So dx is equal to dy over 2r y1 minus y minus 1. And we want to do an integral here. And of course, it is x1 minus, so that is a constant on both sides. And that's equal to x1 minus constant. So that's correct. But now what do we substitute here? Now that we have learned this idea that, oh, there is a cycloid and there is a good chance that that's related. So what do we substitute here? Let's make the substitution, this piece here. So let's make the substitution y1 minus y over r is equal to 1 minus the sine theta. Okay. That's just, at this stage, that's just a substitution, right? But it's of course motivated. That is related. Right? So what is dy? That's minus dy is equal to minus dy is equal to minus r, and that's cosine theta is sine theta d theta. Dy is equal to r. Help me here. I'm messing up, right? So minus dy. So minus of minus cosine theta is plus. Okay. So x1 minus a constant or plus a constant is equal to integral, this time without limits, that limits will be taken care of by the constant there, and we have dy is minus r sine theta, and divided by square root of r over y1 minus y, so that's 2. So y1 minus y over, that's the inverse of that. So it is 2 over 1 minus cosine theta minus 1. Is that correct? Sure, simplify. I think I can get this. So it's x1 minus constant. That's equal to, and I can divide that by r also. And that's equal to minus, let's process this. This is equal to sine theta, d theta, and there's 1 minus cosine theta in the denominator, which goes to the numerator. So that's 1 minus cosine theta over 2 minus 1 plus cosine theta. Plus. So that's 1 plus cosine theta. Not seeing the solution. 1 plus cosine. Actually, because we want this. See if I can pick up.
Substitute
Yeah.
cosine theta to x.
Do you see something here, tell me?
Substitute cosine theta to x.
Oh, but then I will reach some other coordinates, right? The sine of theta x means that will be a new, because I want to stick to theta and x somehow so that I can connect it with the cycloid. It might be possible, I'm not denying that, but let's stick to this because it will come out in this form, like somewhere the structure has to come. But this is just one step as far as I know from here. There's a simplification in here. Is there a simplification? Here, let me refer a bit cheap. Assuming that I can understand my own work. Yeah, this apparently simplifies to cosine. Yeah. Claim is that this integral is just cosine theta minus 1 d theta. So this whole thing simplified to cosine theta minus 1, right? Oh, no, this is sine squared. You were saying the same thing? So this is sine square root of sine square theta. So that's 1 minus the sine square theta, right? Right, that's sine square theta, sine theta, and probably then we see something maybe. Yeah, that's. So there's a 1 plus cosine theta, 1 minus cosine theta, that cancels out. 1 minus cosine theta remains, and that's that. Right. 1 minus cosine theta remains, square of that. So this is cosine theta minus 1 d theta integral. Right. So, okay. That should be clear, right? So I'm not saying the other substitutions that you were thinking will not work. It's just this is, and I want to connect this with as quickly as possible to the cycle. Okay, so here when we said we were integrating from one point to the other, we could have done x1 to x2 and y1 to y2, right? That would have been okay. And here now we want to invert it in terms of y then, right? We want to write everything in terms of y. So in preparation of that, that integral is doable. That is sine theta, right? So that's sine theta minus theta. Then you already see the connection x1 minus this is this, right? So in principle, this is done here at this point because you have this relation here. That was your substitution, and your x1 minus a constant over r is sine theta minus theta. That's this, right? So those two immediately tell you that it's a cycloid. But let's process this. One way of doing this is that you have to evaluate this from theta 1 to theta 2, or let's say from y1 to y2, and this will be then equal to. Now x2 minus x1 then, right? So this will be x2 minus a constant. So this will be x2 minus x1 over r. Right, if I go in the right way, so this is okay as we did it because this is some constant, but this is x2 minus x1 over r when I go from final to initiate. And then write theta, and because I want to, theta is given in terms of, according to our substitution in terms of cosine. So it's good to write sine theta as cosine theta. So it is 1 minus cosine square. That way, theta when you replace, you can immediately replace it. So what is this meaning? So this is x2 minus x1 over r equal to 1 minus cosine theta is 1, cosine theta is 1 minus by 1 minus y over r square. Cosine square. Square. And then take a square root if you want. I'm just replacing cosine theta there here. Minus theta, which is cosine inverse. So it is cosine inverse of 1 minus y1 minus y. And this one has to be evaluated between y2 and y1. Well, now I should go back to the x1 minus 1, because otherwise I have to process this y2 minus 1. Is that the same answer? Sine inverse of this minus, yeah, so if I go back, change my mind. So that this is x minus a constant, right? X minus a constant over x minus constant over, let me call it x minus x1 over x minus x1. So that's x1. So then I don't have to do same idea. I think last lecture also I messed up there or messed up, or it's just a choice. And now it is okay. I bring this here, square it, square this. So it is x minus x1 over r minus of cosine inverse of 1 minus y1 minus over r squared plus 1 minus equal to 1. This quantity plus this whole thing squared. And that should be the cycle. Yeah, that's exactly. Well, struggled a little, but worked out. So, moving. But this was mostly algebra, but still a good piece in the sense of cycloid shows up here and there. Still to have that observation. Any questions? So that's the answer that whenever you want, this actually goes through a cycloid connecting the 2 points. There are many cycloids given 2 points. There is always a cycloid. Pretty. There is also, whenever you think of a cycloid, I like to mention the following, and this is a pretty clever thing that was invented. Remember that historically, since Galileo, it was a big thing to maintain time. Like once Galileo realized that a pendulum can be used to keep time, and that was the first time that you started maintaining time using a pendulum. And time is significant because if you're moving in a ship, also you can keep a pendulum, and if you have 2 such pendulums, you can have a reference. You can say which or the longitude can be maintained using time. Like you start with a pendulum, keep it at one sync, and then start another pendulum at another time, and you can maintain time in that, or you can talk about longitude in that manner. And in general, there is a lot of applications of timekeeping, and in those days, we are talking about 1500s, right? During the time of Newton, if you could invent a time machine, or time means something that maintained time to, let's say, second digit accuracy, you're cool. Like that's a great advancement. Even today, we do a big deal with time, but these days we talk in terms of what 10 raised to minus 18 seconds, and so those are the accuracy we have. But so then the point is, then when you talk about a pendulum, the biggest disadvantage is that the biggest disadvantage you have with a pendulum is that the solutions that's your angle theta. If you want normal t is how much? 2 pi L over G, right? So the length L of this over G. Right. I think that's correct. This is true only for small angles. Theta has to be very much smaller than 1. Theta is a dimensionless quantity. 1 means 1 radians. 1 radian is about 57 degrees. Significantly small. That means if you want a 1% accuracy, then you want to stick to 10 degrees and so on. So if you want to extend this, you would say that, okay, I want to be able to do this for finite angles, and you can do that. This becomes a Bessel function. K0 of some quantity here. This is a function of theta. Right, so this is some function of theta. It's not really theta. I think it is sine of theta over 2 or something. So that is, this is Bessel function, modified Bessel function. But then it is not really convenient, right? If you first of all, t is not constant. It's not a very good keeper of time when you have a normal pendulum. So this is when Hoyen, I don't know how to pronounce this. How do you pronounce this? Hoyen's. Is that S? Sound? That's enough. Yeah. I think Hoyen's probably that I used to say. I guess like when I was young, I think Hoyen's. And again, during the time of Newton, so he came up with this brilliant, very clever that if you have a cycloid-shaped structure, so this is, let's say, and you can build this. I mean, if you can build this in your lab, that would be cool. Like actually, we like there was this high school student, it was the 8th or 9th grade in Philadelphia. He's my wife's friend's son. We suggested that he actually printed this on using a 3D printer, and he actually made it and compared. So now the idea is that instead of having this pendulum here, you actually hang the pendulum here. Okay. Now the point is, as you swing this, the length of the pendulum gets shorter. As you move this side, the length gets shorter and shorter by a certain amount. And by the way, this is cycloid. Like this is that wheel rolling, right? So this is that cycloid structure. And the same thing on this side. And this change in length is always in such a way, if you make this cycloid of the correct property related to this length L, this change in length is in such a way that this will actually go away. The Bessel function will go away, and time period comes back to 2 pi L over G. So you can again maintain time. It was very clever, but again, I think it was never, as far as usage goes, it did not click. There were other challenges, I suppose. It's not that that became the way to do that, but very clever. I mean, just, at least it's a cool result. Doesn't depend on the angle. And it can be covered like this is, yeah, if you want, if you look up, I think you will see solutions to this. This shows up in Sommerfeld. I think that's a reference that I suggest for this course. Sommerfeld's mechanics. Sommerfeld mechanics. Covers this example very nicely. Sommerfeld is advisor of Pauli, Heisenberg, all this very. It was Sommerfeld's school that started quantum mechanics and relativity. There was a lot of activity in the very nice students of the school. So it is. You say Sommerfeld's lectures. So those books are almost on every subject. It's kind of. So yeah, with that story, any comments? Yeah, I struggled a little bit with that, but
Is this the last session for the exam?
I think so. Yeah, I mean, strictly speaking, yes, let us say exam will cover everything till today. But as I said earlier, whatever I'm going to do on Tuesday is going to be also functional derivative. We're going to have functional derivative for quite some time. So I can always ask whatever I'm planning to teach on Tuesday in the context of functional derivative. So yeah, to answer your question, yeah, exam will cover everything until today. But be open, you won't lose like studying one more case. But yeah, I do understand as a student, you get confined to that part. And just if you've done your homework seriously, and you try to understand every step, then you should be fine. At least that's the way I myself, that's how I try to prepare the question. But I realize that my exams, either you get it or don't get it, kind of. It's not the easiest step. Even though I try to make it easy, it's easier to say that. Don't stress too much. Thank you.